What if a road could tell you it was breaking? Right now it cannot. We only see the damage when it is too late. Cracks appear, potholes form, traffic slows to a crawl. The methods we use to check on our roads are old, they are slow and expensive. Workers drive out to a site, they look at the surface, they might see some small cracks, but the real damage, the deep structural failure, is invisible. It lurks beneath the asphalt, growing with every truck that rumbles past. To find these hidden problems, engineers have one main tool. They drill. They cut out a cylindrical piece of the road, called a core sample. This piece is taken to a lab. There, it is tested for strength and integrity. This process is incredibly disruptive. It requires closing lanes. It creates traffic jams. It is also a destructive act. The very act of checking for damage creates a new hole that must be patched. You take one snapshot in time, from one tiny spot. The road could be perfectly fine a few feet away, or it could be on the verge of collapse. It is a guess. This guesswork is a fundamental problem for infrastructure management. Road authorities have to make big decisions with very little data. Do they spend millions resurfacing a highway this year or next? Is a small crack just a cosmetic issue, or a sign of a deep fracture about to fail? The wrong decision wastes money. It puts drivers at risk. It leads to emergency repairs that cause massive disruptions. For decades, this has been the accepted reality. We have built smarter phones and smarter homes, but our roads have remained stubbornly dumb. Now, that might be changing. A team of researchers in Germany is pioneering a new approach. It does not involve drilling. It does not involve guesswork. It involves a special kind of fabric. They have developed a textile that can be embedded directly into the road. This fabric acts like a nervous system for the pavement. It can feel the stress and strain caused by traffic. The core of this new technology is surprisingly simple. It is a fabric woven from flax. Flax is a natural plant fiber. It is the same material used for centuries to make linen cloth. It is strong. It is renewable. It is also inexpensive. These qualities make it an ideal candidate for road construction at massive scale. The researchers did not just use plain flax. They wove something extra into the textile. A grid of ultra-thin conductive wires was integrated. These wires give the fabric its sensory abilities. The metallic wires are incredibly fine, under a millimeter. They are woven alongside thick, tough flax yarns. The flax provides structural support. It holds the delicate wires in place. It gives the fabric the strength to survive road construction. Weaving happens on industrial looms like other textiles. The process can be scaled up easily. The fabric can be produced in long, continuous rolls for sites. It looks like rustic, heavy-duty cloth but functions like a high-tech sensor. The textile design is critical. Yarns must be spaced so hot, asphalt binds through the fabric into lower layers. If the weave is too tight, layers could separate. A new weakness. The fabric must withstand pavers and heavy trucks during installation. So, how does a piece of cloth feel a truck drive over it? Well, the answer lies in a basic principle of physics. When you stretch a metal wire, its electrical resistance changes. The change is tiny, almost imperceptible, but it is measurable. When a car passes over the road or a truck passes over the road, its immense weight causes the pavement to flex and bend ever so slightly. Because the smart fabric is embedded within the road structure, it bends and stretches right along with it. This stretching action tugs on the thin, conductive wires woven into the flax. As the wires stretch, their electrical resistance increases. When the load is removed and the road returns to its original shape, the resistance drops back to normal. These fluctuations are the raw data. Sensor nodes are connected to the edges of the fabric grid at the side of the road. These nodes continuously send a small electrical current through the wires and measure the resistance. Every vehicle that passes creates a unique electrical signature, a blip in the data stream. The system can capture thousands of these events every day, building a detailed picture of the road's behavior under stress. This data is then sent from the roadside collection unit to a central server for analysis. This is where artificial intelligence comes into play. An AI program is trained to understand what a normal signal from a healthy road looks like. It learns the typical resistance patterns created by different types of vehicles, small cars. The practical application of this technology has been carefully considered. The fabric is designed to be integrated seamlessly into the standard road building process. It is manufactured in wide rolls, typically around 50 centimeters, but adaptable to different needs. After the gravel base layer is prepared, the fabric is simply unrolled and laid down. Multiple strips are placed side by side to cover the road width. The material is light enough to be handled by a small crew. No special heavy gear needed. Once in place, the rest of construction proceeds as usual. Hot asphalt, often over 160 degrees, is poured directly on top. The flax composition and weave spacing withstand that thermal shock. Heavy pavers and rollers drive over it to compact the asphalt, tested to ensure it does not slip, tested to ensure it does not tear, tested to ensure it does not bunch up. Thin sensing wires are protected by surrounding flax fibers, keeping the grid functional. They installed the smart flax fabric in a road at an industrial park in Germany. That site was chosen for heavy, consistent truck traffic, a real stress test. Measurement nodes were put along the roadside to collect 24/7 data. The trial validates durability and data reliability in a live environment. Variable, weather. Variable, temperature changes. Variable, different vehicle types. The system is capturing strain data from passing vehicles. Researchers are using that data to refine their AI. Teaching the software, heavy truck on a cold day. Teaching the software, light car on a hot day. This reduces false positives. The benefits of this smart fabric system are clear and compelling. The most immediate advantage is the move away from destructive testing. Instead of drilling holes to guess at a road's condition, authorities can get a continuous, live feed of its structural health. This non-invasive monitoring allows for a proactive rather than reactive approach to maintenance. Planners can identify weak spots and intervene with targeted repairs before a small crack becomes a giant pothole. This stitch-in-time approach saves significant money on materials and labor. Furthermore, this technology promises a dramatic reduction in traffic disruption. By knowing exactly where the problem is, repair crews can work on smaller sections with greater efficiency. For the public, this translates directly into fewer lane closures, shorter delays, less frustration. The economic savings extend beyond the road agency's budget. Less traffic congestion means less wasted fuel, less lost productivity for commercial transport, a smoother, safer journey for everyone. The use of flax as the primary material offers a significant environmental advantage. Flax is a renewable resource, requires less water, fewer pesticides to grow than many other crops. By replacing more resource-intensive materials, it introduces an element of sustainability into road construction. This smart fabric represents a paradigm shift in how we manage our essential infrastructure. The road ahead may soon be able to tell us exactly where it hurts, and for the first time we will finally be able to listen.